start a new one. So far, we have dealt with acceleration from a change in speed in terms of numbers. But now, we will deal with acceleration. Well, how else can you accelerate other than changing your speed?
Changing direction.
Let's deal with that. All right, so I have an object that's constantly changing directions. So in other words, it's traveling in a circle. So speed is constant. And travels in a circle. So you got cruise control on a flat road. At this point, at any point, we're traveling like that. I'm going to call that V initial and V final. So let's figure out what the acceleration is. Well, how do you find acceleration given the initial and final velocity?
Oh, you would, what is it? Find the average and then multiply it by time?
That would be displacement.
Do we know time?
And time, we don't know time, but time actually is going to cancel out. But how do you find acceleration?
Well, you use one of the K formulas.
Okay, which one do you want to use?
I guess VF equals VI plus AT.
Okay, so VF equals VI plus AT. If I subtract VI from both sides, I get VF squared minus VI squared is equal to AT. And so my acceleration, which is a vector there, acceleration is my change in velocity over however much time. Now this is average acceleration, but it's at no loss that we could do the calculus version. This is the non-calculus version of the derivation. So if this angle here is phi, well, I need to find the change in my velocity, so in order to do that, I really need to break this up into components. I need to know what that angle is. And what is that angle? I know that that is a right angle there. Geometry. So I've got some central line there. I really can't. So that's phi. That's the direction of velocity there. And I'm trying to find that angle right there. And I know that that is a right angle.
So the angle would be 90 minus 5?
This one here?
Yes.
Well, let's find out. So we have a speculation there that this is the complement of phi, which I'll label as phi prime. All right, if that's, so I got a right triangle here, this bigger one. What would this angle here be? Looking at
90 minus
that triangle. Yeah, that would be 90 degrees minus phi, or whatever, minus phi prime. Now let's look at the smaller triangle. That's a right angle there,
so 90 minus 5 prime.
which would be all right, so that is 90 minus phi prime. Phi prime is just 90 minus phi.
It's 5.
Yeah, this angle and that angle are the same. If you draw it with more skill, you can see that this is the skinny angle, that's a skinny angle, and as we get closer and closer to the vertical, this becomes skinnier and skinnier, as does that. So they do go hand in hand. So what I have here then is, well, it's a shared process. This is V, so that's phi. This is VI cosine phi. And this is VI sine phi. Go through a similar logic over here. We have VF cosine phi, VF sine phi. It's not theta, it's phi. So now let's find the difference.
Why are we using 5 instead of theta?
It was my mood.
Okay.
We're going to have a point later on where I need to use a second symbol for angle, and so I'm choosing phi for this one and theta for the other one. All right, so VF minus VI is, well, that's my change in velocity, is equal to, this is VF cosine theta, cosine phi I hat, minus VF sine phi j hat, minus VI cosine phi I hat plus VF sine phi j hat. We don't need this thick. What does that equal to?
How do you get that equation?
So I broke VI into perpendicular components, horizontal and vertical. You good with this being cosine and then sine?
Yeah.
All right. So I define my I hat, j hat like that. So this is, make sure I didn't do something silly over there. All right. So it's VI cosine phi I hat, VI sine phi j hat, plus in between them. Over here, this one's going down, so that's why it's negative. So this is my VF, and this is my VI.
Oh, okay. Just, is that supposed to be VF sine?
That's an F. That's a plus. What's the breakdown here?
Okay, so I'm just confused by the first one is VF minus VF, and then the second one is VI minus VF, or plus VF.
Oh.
Okay.
Thank you very much. Sorry about that.
And why is it minus on the first one and plus on the second?
All right, so change is always final minus initial. My V final, given the way I've set up my coordinate system here, V final is to the right and down.
Oh,
Because I passed the vertical, so it's slightly that way.
yeah.
Okay. Flashback to grad school. The board was filled with letters, and I was the only student in the class. And he miswrote something, and I was trying to point out in the C of the alphabet C. And so eventually I just stood up and I walked over and I said, "Should this be," and whatever letter it was supposed to be. And he goes, "Oh, yes." And I was still standing there as he was talking about it, and he looked really uncomfortable. He goes, "Have a seat." I said, "No, I'm fine." "No, sit down." I looked at him strangely. "I lecture, you take notes, that's the way it is." I dropped that class that day. Flashing back to, if you will come up here and point it to it, I'm fine with that. Sorry, I digress. His reasoning was, if another student joined the class, it would not be appropriate for me to stand there. Then the two of us to have a conversation with that. Leave high school. All right, so what is this equal to?
The change of velocity.
Yeah, if you work through the math, what do you end up with? I did A minus B minus A plus B. Oh, I see potentially another problem here. The speed is constant. VI is equal to VF. So we could go so far as to just get rid of the subscripts there. So although I did not intend to write F before, I wasn't technically wrong. But how about that?
You would get negative V sine of, what were we calling it again?
Phi.
Phi times 2.
J hat. All right. So we now have our change in velocity here, because the horizontal component doesn't change at all the way I've set it up here. Oh, you know. And all sorts of little things. And so I know that my acceleration, therefore, is -2v sine phi over time, however much time passes, in the j hat direction. Doesn't really help us a whole lot at this point, but we can take it one step further. Since I really want to figure out what is the acceleration at this point right here, what I'm going to do is I'm just going to let phi get smaller and smaller. So I drew it out like that because it gives me more room to write, but really I want to make phi tiny. So as phi goes to 0,
you get 1. Oh, sorry.
How do we get 1?
Sine 0
Is
0.
yeah, so that would sort of spoil it if we just said, if we went that far and said, well, this is close to 0, therefore the acceleration is 0. There's no acceleration with change in direction. There's a different approximation. Any of you got into the Maclaurin series or Taylor series?
Yes.
You remember the name?
No, yeah, I remember it.
That was the one part of Calc 2 I had trouble with.
Yeah.
Maclaurin series.
I always get Maclaurin and Taylor mixed up. I think this is the simpler one is Taylor or Maclaurin?
Taylor was easier.
Okay, so Taylor series. Do either of you remember the Taylor series for sine? If you take the derivative of it, you would get 1 minus, well, the 3 would come down, so you get phi squared, and that 3 would cancel out with the 3 there, so you'd end up with 2 factorial plus phi to the 4th over 4 factorial minus phi to the 6th over 6 factorial, and so forth. This is the derivative, and the derivative of sine is cosine. So, if phi is small, phi is not 0, but if phi is small, recognize that this cube term is incredibly tiny. The 5th term even smaller, the 7th term even smaller, or the 7th power even smaller. So if phi is small, these terms become so incredibly inconsequential. So we're going to use, and this is something that shows up more than once in here, the small angle approximation. If phi is much less than 1, so the 2 less than symbols mean much less than. I don't have units here, so this is much less than 1 radian. Then phi is approximately equal to the sine of phi, which is approximately equal to the tangent of phi. That is the small angle approximation. So we have acceleration is -2v sine phi j hat over time. Give myself clearing some space there. Since we are going to look for the acceleration at that peak, we're letting phi become smaller and smaller, we can now take my acceleration there. Acceleration, therefore, is close enough to -2v phi over time j hat. And I have it in here.
diagram I'm looking for that I can't seem to find it.
All right, don't worry about it then. All right, we are dealing with phi and radians here. So we have to somehow deal with this time. It's the time it takes to get from here to here. So if it's traveling at a constant speed over that amount of time, how far is it going to go? What is that arc length if it's traveling at some speed v for a certain amount of time t? If you're traveling at a constant, if you travel at 50 meters per second for 10 seconds, how far did you go? Yeah. So if I'm traveling at some speed v for some time t, how far did I go?
VT.
Yeah. So this distance here, from here to here, is just vt. That's also the arc length. What's the relationship between arc length and the angle? I take any circle. I have some angle theta here, I have some arc length, we'll call it s, and some radius of r. What's the relationship between theta, s, and r? Assuming theta's and radians. We're about to lose chance here.
Sorry.